Hello and welcome back. In this video I'll make a complete proof of the Gaussian integral, or I'll actually compute it. I don't know if I'll exacerbate it, but yeah, let's dive right in. So to justify the improper double integral and equating the two expressions, we begin with an approximation function. Now I'm assuming that everyone knows what Gaussian integral is, but anyway. Let I of a equal to the integral from minus a to a of e to the negative x squared dx. And then, if the integral from negative infinity to infinity of the same integrand dx were absolutely convergent, we would have that its Cauchy principle value, that is, the limit as a approaches infinity of IA, would coincide with the integral from negative infinity to infinity of e to the negative x squared dx. Well, to see that this is the case, consider that the integral from negative infinity to infinity of the norm of e to the negative x squared dx is less than the integral from negative infinity to negative 1 of negative x times e to the negative x squared dx plus the integral from negative 1 to 1 of e to the negative x squared dx plus, finally, the integral from 1 to infinity of x times e to the negative x squared dx is less than infinity. So we can actually compute the integral from negative infinity to infinity of e to the negative x squared dx by just taking the limit as a goes to infinity of I of a. So taking the square of I of a yields I of a squared is equal to, parentheses, the integral from negative a to a of e to the negative x squared dx times, parentheses, the integral from negative a to a e to the negative y squared dy. And this is without loss of generality. We're just introducing a new variable. Yeah, it could be z, it could be x, it could be r, whatever. This is equal to the integral from negative a to a of the integral from negative a to a of e to the negative y squared dy times e to the negative x squared dx, which is simply equal to the double integral both from negative a to a of e to the negative, parentheses, x squared plus y squared dy dx. And then we can use something called Febini's theorem, and the above double integral can be seen as an area integral. So this is the double integral, and then you write like this: square brackets, and then put negative a, and then you cross it with the exact same thing. So this is equal to the exact same thing, but instead of having an upper and lower bound, you introduce an area, and as well, instead of dy dx, you have d of x and y. And taken over a square with vertices, the set of negative a and a and a and negative a and negative a and negative a as the xy plane. And since the exponential function is greater than 0 for all real numbers, it then follows that the integral taken over the square's in circle must be less than I of a squared. And similarly, the integral taken over the square's circumcircle must be greater than I of a squared. And the integral over the two disks can easily be computed by switching from Cartesian coordinates to polar coordinates. So let's define x as r cosine theta and y as r sine theta. If you know some trigonometry, this should be really fundamental, but anyway. And then we can define the Jacobian matrix of r and theta as the matrix partial derivative of x with respect to r, partial derivative of x with respect to theta, the partial derivative of y with respect to r, and the partial derivative of y with respect to theta. And yeah, computing these derivatives, we simply get cosine theta, negative r, sine theta, and r cosine theta. And we can then calculate d of x and y as the absolute value, or the norm, of the Jacobian matrix of r and theta times d of r and theta, which is simply equal to r times dr of theta, or we can rewrite it as the integral from 0 to 2 pi, integral from 0 to a, of r e to the negative r squared dr d theta is less than I squared of a, is less than the integral from 0 to 2 pi, integral from 0 to a times the square root of 2 r e to the negative r squared dr d theta. And by integrating, we can get at pi times the parentheses 1 minus e to the negative a squared is less than I squared of a, is less than pi times parentheses 1 minus e to the negative 2a squared. And then, applying the squeeze theorem, this gives the Gaussian integral, namely the integral from negative infinity to infinity of e to the negative x squared dx equals the square root of pi. Thank you for watching, have a nice day.